This video, which I hope will be a short one in comparison to the others, is an introduction to a definition which we need to go on and cover the material on orthogonal complements. So this video is not about orthogonal complements, it's about a particular concept we need for that. This concept is called the notion of a direct sum of subspaces. This notion of a direct sum gives us a way, in a sense, to take two subspaces of a vector space and add them together. And we'll see what we mean by addition of subspaces. So first, a preliminary definition. Let V be a vector space, and let W1 and W2 be two arbitrary subsets of V. W1 and W2 may or may not be subspaces. They are just subsets contained in V. Then we'll define the sum of these two subsets. The sum of W1 and W2 is, well, it's denoted W1 plus W2, and it is defined as follows. It is the set of all elements of the form x plus y, where x is in W1 and y is in W2. So essentially we're just taking all possible sums where we choose the first element to be in this vector or this subset, and the second element to be in this subset. Here's a very brief example. Let V be the vector space R2, and take as W1 and W2 the following subsets. W1 is a subset consisting of just two vectors, 0, 0, and 1, 2. And W2 is the subset consisting of three vectors, 0, 0, 2, 2, and 2, 3. So let me first emphasize that neither W1 nor W2 are subspaces at all. They fail miserably at any test you want to throw at them for being subspaces. They're not closed. Well, actually, no, they're not closed under vector addition. They're not closed under scalar multiplication. They are far from subspaces. If you wanted to draw W1, you could. W1, for example, just consists of two singular points, the point at 0, 0 and the point at 1, 2. So it's those 2 points. There's W1. It's not a subspace. And similarly for W2, it's just a collection of 3 points. But we can still form the sum of these two sets, W1 plus W2. And to do so, we just take all sums of the following form. We take a thing up here, and we add it to anything down here. So, for example, I could take this thing right here, and add it to this thing right here to obtain 0, 0. I could take this thing right here and add it to this thing right here to obtain 2, 2. I could take this thing right here and add it to this thing right here to obtain the vector 3, 4, and so on and so forth. I simply take any possible vector up here and add it to any possible vector down here. And if I complete this process, I get the following set of 5 vectors. Of course, this thing's not a vector space either. It's not closed under vector addition or scalar multiplication. It has only finitely many elements, 4 of them to be precise. Let's look at another example where the vector space is again V equals R2. But this time let's take for subsets subspaces W1 and W2. Here W1 is the subspace spanned by 1, 0. And W2 is the span of the column vectors 1, 0 and 0, 1 in R2. So as another brief exercise, let's consider the sum of these two subspaces W1 and W2. So for the sum of these two subspaces, W1, W2, I take any vector in W1. Now remember, W1 is the span of this vector. So any vector in W1 looks like, some scalar multiple of 1, 0. And then any vector in W2, and since W2 is the span of these two vectors, any vector in W2 looks like some linear combination of these two vectors. So here's a thing in W1, and here's a thing in W2. So anything in W1 plus W2 looks like a sum of these two things. So I get this set right here, where R, S, and T can be any scalars. Now, you may notice one important thing. There's some redundancy in this set. I'm taking any scalar multiple of 1, 0 here, and I'm taking any other scalar multiple of 1, 0 here. I don't actually have to write both of those. Another way of saying this is that the sum W1 plus W2 is contained in the span of these two vectors here. So we could write W1 plus W2 is in fact the span of the vectors 1, 0, and 0, 1. So we just get W2 all over again because there was some redundancy in that set. But that's okay. That's the definition of the sum. It's just an example. But there is one important feature of this example which we did not see in the previous example, and we'll single it out. We started this time with two subspaces, W1 and W2, and we note that when we take their sum this time, we do get another subspace of R2. And that's not just something that happens in this example. That, in fact, is something which happens in general. If we take two subspaces and add them, and take their sum, I should say, then we get another subspace. That's a theorem, and we'll write it down briefly here. The theorem reads, if W1 and W2 are both subspaces of some vector space V, then their sum is also a subspace of V. We won't prove this theorem here. You can find the proof in your text, and it's a straightforward proof. We can simply use what I've called the subspace criterion before. That is, just show that this sum of subspaces is closed under vector addition and scalar multiplication. And that's the proof of the theorem. But we'll move on now. We want to address the case when we don't have a redundancy like we saw in this example. And that turns out to be a special kind of sum of subspaces. And that's the main point of this video. So here's the definition we really want for this video. Let V be an arbitrary vector space, and let W1 and W2 be subspaces of V. If these two subspaces satisfy these two conditions, 1, that the sum of W1 and W2 gives you all of V, and 2, that the intersection of these two subspaces is the 0 vector space, then we say that V is the direct sum of W1 and W2, and we have special notation for this situation. We write this as V equals W1, I call it circle plus W2. We say that V is the direct sum of these two subspaces. So let's look at a brief example where a vector space is the direct sum of two of its subspaces, and one where it's not. For this example, let's take V to be the vector space R3 and consider the following two subspaces,